Back for another video lecture with me, Dr. Scott Spaniel, your instructor for Math 141 Statistics at Morton College. If in most of my classes, we are now entering the last chapter that we're going to cover for this course, chapter 4. So we've kind of saved this to the end because it concerns comparing two variables, which most of the course is about comparing one variable. Looking at a single variable. And if it's, for some of you, this will be your fourth chapter, but for most of you, this will be the last chapter we're going to cover. So we're going to cover sections 4.1 today. And 4.1 is about scatter diagrams and correlation. So the general idea here is this is a type of variable you actually see quite a bit when you read about studies, especially in the general news media. Is they're talking about correlation. So they're comparing two variables to see if they're related to one another. And this is one way to do that. So let's go ahead and switch over to our note sheets and we can take a look at that. So once again, these note sheets, just like always, are either on my Math Lab or Blackboard, depending on how your course is set up. And we're going to start right here on page 2. So a response variable is a variable whose value can be explained by the value of the explanatory variable. These are also often called the response variable, can also be called the dependent variable, and the explanatory variable is also called the independent variable. And the idea here is that the explanatory variable can be anything, but then the response variable is a response to the explanatory variable, so it's dependent. It depends on what the independent variable is. For this course, we're going to use response and explanatory, but in other classes, you may have seen things like dependent and independent. A scatter diagram is a graph that shows the relationship between two quantitative variables measured on the same individual. Each individual in the data set is represented by a point in the scatter diagram. The explanatory variable is plotted on the horizontal axis, which is also called the x-axis, and the response variable is plotted on the vertical axis, which is also called the y-axis. Two variables that are linearly related to one another are said to be positively associated, or let's go ahead and use the word correlated. Positively correlated when above average values of one variable are associated with above average values of the other variable. That is, two variables are positively associated if whenever the value of one variable increases, the value of the other variable also increases. Two variables that are linear related are said to be negatively correlated when above average values of one variable are associated with below average values of the other variable. That is, two variables are negatively associated if whenever the value of one variable increases, the value of the other variable decreases. Okay? So that's the idea there. So here are some examples of what these might look like, right? So here's an example of a linear correlation, right? That's positive. This would be a positive one because these values follow a fairly straight line that goes in a positive direction, has a positive slope. Here's a negative example of a linear one, right? Because it makes a negative slope. As one variable goes up, the other one goes down. As the x value gets bigger, the y values get smaller. These next two are examples of nonlinear relationships, which we're not going to talk about in this class, but are other correlations that you could talk about. And then the last one is where you'd have no relation, where they're just kind of all over the place. So here's an example of a scatter diagram. So this scatter diagram was drawn in mini tabs, shows the relation between the percentage of the population of a state plus Washington, D.C. that has at least a bachelor's degree and the median income of the state in dollars. So does it look like any relationship exists between education and median income? Well, it looks like there is some sort of positive relationship, right? These kind of all follow this line. They're scattered about it, but they all kind of follow a line that goes up and to the right. So it looks like there's some sort of positive relationship or correlation going on. There is over here, though, one outlier. That one observation that sticks out from the rest. This particular observation is Washington, D.C. Can you think of any reasons why Washington, D.C. might have a higher percentage of residents with bachelor's degree but a lower than expected income? Well, there's a high percentage of government jobs in Washington, D.C. per capita, and government jobs tend not to be as well paid as private sector jobs for the same level of education. So that's kind of the idea there. In fact, there's a lot of people in Washington, D.C. that are interning who make almost no money but have bachelor's degrees or higher level degrees. Okay, so that's the idea. So what we want to do to start out here is, first off, look at what we just think the relationship for these things would be. So there's a positive correlation, negative correlation, or no correlation. And there's no necessarily right or wrong answer here, but what we want to be able to do is be able to support our response. So like, for example, number of children in the household under the age of 3 and expenditures on diapers. So if you had, the way to think about this is if you had more children under the age of 3, which I did not spell anywhere near close, any children under the age of 3 in the house, if you had more of those children, the question is, would you have more or less, or is it impossible to tell, expenditure on diapers? And the answer to this is most likely more, right? So that would be a positive correlation. Okay. So the second one says if interest rates on car loans and number of cars sold. So if the interest rate increases, is the number of cars sold going to increase as well, or would it decrease, or is it impossible to tell? And in this case, I think the answer would be decrease, right? If interest rates on car loans go up, it's more expensive to buy a car, so fewer people are going to decide to buy a car. Some people still will, but not most people. A lot of people won't that might have. So this will be negatively. That's a negative. Hold on. That's a negative correlation. Okay, so that's the idea there. Number of hours per week on the treadmill and cholesterol level. So as you spend more hours on the week, more exercise can bring down cholesterol. So most likely, if you spend more time on a treadmill, your cholesterol will be lower. So that would be a negative correlation. Okay. Price of a Big Mac and the number of McDonald's French fries sold in a week. So if the price of a Big Mac goes up, are people going to buy less Big Macs? Probably. If people buy less Big Macs, are they also probably going to buy less French fries? Possibly. So I'd probably also call this one a negative correlation. And then shoe size and IQ would be no correlation because there's nothing about those that are related. Okay, so that's the idea behind this. So why don't you guys pause the video for a second and see what you get for these ones. Okay, so now that you've had a chance to try these, let's run through them together real quick. So number of cigarettes smoked by a pregnant woman each week and birth weight of a baby. This one actually has a negative correlation. You might be able to guess that because smoking is bad in general, but it's also bad for a woman who's pregnant. And one of the things it can do is lower birth weight. Years of education and annual salary. This probably has some sort of positive correlation because more you go to school, the more likely the higher your salary is probably going to be. Now that won't always be the case, right? But it definitely could be. Number of doctors on staff at a hospital and number of administrators. This is probably a positive correlation because if you have more staff at a hospital, more doctors on staff, you probably need to have more administrators to administer those doctors. Head circumference and IQ scores is going to be no correlation. And number of movie goers and the movie ticket price. These are probably negatively correlated. Because if the movie ticket price were to go up, the number of people going to the movies would probably go down. Okay, so that's the idea of kind of what kind of variables are going to have these correlations. Now, there are all kinds of correlations that aren't real, which is one of the things you have to watch out for when you're dealing with these. Just because two things are correlated doesn't necessarily mean there actually are correlations. Okay, so here's some examples. These are going to be really weird. I just Googled this right now. So, U.S. spending on science and space technology and suicides by hanging, strangulation, and suffocation. They have a very strong correlation. They are not at all actually related to one another. Number of people who drowned by falling into a pool and films Nicolas Cage appeared in. Okay, right? These are, once again, have a pretty strong correlation. They follow a pretty similar curve, but they're not actually related. Just because Nicolas Cage is in more movies doesn't mean more people drown by falling in a pool. Doesn't cause one. Per capita cheese consumption, the number of people have died from being tangled in their bed sheets. Okay, so what these are all good examples of are things that correlate but are not actually caused by one another. And that's one of the things we want to be really careful with when we are looking at these different values and doing these problems. Is there's a very big difference between correlation and causation. So just because two things are correlated doesn't necessarily mean they're caused by one another. Okay. The linear correlation coefficient, or the Pearson moment correlation coefficient. So most of the time we just refer to it as the linear correlation coefficient, but its full true name is the Pearson moment correlation coefficient. It's named after, I believe, his first name's Daniel Pearson, who came up with it. Came up with this formula that we're about to look at. So this is a measure. It's a measure of strength and direction of linear relationships between two quantities. And I'm going to give you the formula here, but in no way do you need to know this formula. We're not actually going to use it. But we use the Greek letter rho, which is like kind of an italicized P, to represent the population correlation coefficient, and lowercase r to represent the sample correlation coefficient. The formula for this is the sum of all the x sub I minus x bars over s sub x times y sub I minus y bar over s sub y all over n minus 1. So basically what this formula does to get a correlation coefficient is it takes the sum of all the z-scores of the x values times the sum of all the z-scores of the y values, and then it divides by the n minus 1. That's all that really says. You're never going to have to do that by hand. Okay, but that is the formula if you're at all interested in that. So some properties of the linear correlation coefficient, these are important. First, linear correlation coefficient is always between -1 and 1 inclusive. That is, -1 is less than or equal to r, which is less than or equal to 1. Okay? If r equals 1, then a perfect positive linear relationship exists between the two variables. So the scatter diagram will be a perfect line. If r equals -1, then a perfect negative linear correlation relation exists between the two variables. So just to look down here at those real quick. Here is an example of r equals positive 1, and here is r equals negative 1. Notice they make a perfect straight line, one with a positive slope and one with a negative slope. So the closer r is to positive 1, the stronger the evidence is of a positive association between the two variables. The closer r is to negative 1, the stronger the evidence of a negative association. So you want to be close to 1 or negative 1. And then the negative or positive tells you the direction. If r is close to 0, then little or no evidence exists of a linear relation. The key word there is linear. You can have things that have very small r-scores that have a relationship, they're just not linear. Because linear correlation coefficient is a measure of strength of the linear relation, this does not imply no relation, just no linear relation. And then the linear correlation coefficient is unitless measure of association. So the unit of measure for x and y plays no role in the interpretation of r. So r does not have a unit. The correlation coefficient is not resistant. So this is a word we haven't used in a while. But it means, therefore, an observation that does not follow the overall pattern of the data could affect the value of the linear correlation coefficient. So outliers have a strong effect on this value. And so here's some examples of correlation. So here's a strong positive, right? It isn't perfect, but they do follow very strongly that line, follow a line. Here's a moderate one at 0.4. You could tell it has some relationship, but the dots are kind of all over the place. Here's a strong negative, moderate negative, and here are two examples of no linear correlation. You've got one where the dots are just all over the graph, and then you've got one that follows a pattern, just not a linear one, right? This follows some sort of like parabola or something like that. Okay, and so that's what we're going to be looking for. So let's go ahead and practice doing this kind of idea using our calculator. So an engineer wanted to determine how the weight of a car affects gas mileage. The following data represent the weights of various domestic cars and their gas mileage in the city for the 2008 model year. Okay, so we've got different cars and then their weight. And then their mile per gallon. Determine which variable is likely explanatory variable and which is likely the response variable. Okay. So which one of these do you think? Does miles per gallon determine how much the car weighs? Or is it more likely that the weight could be a determining factor in how many miles per gallon the car gets? And it's most likely that second one. So the explanatory variable is going to be weight, and the response variable is miles per gallon. Okay. Now we want to draw a scatter diagram. This question, what type of relation, if any, appears to exist? You can ignore this. That's from a different question. But we can still do it. So let's talk about how to draw a scatter diagram. So like always, I went ahead and this data is in our Math 141 note sheet data set. So if I go all the way to the end to 4.1 problem 1, and I copy and paste this data into my graphing calculator, and then if I hit the little zoom thing in the left corner of that box, it does the rest for me. Okay? So it goes ahead and it draws the scatter diagram. And if I try to zoom out a little more, I can see it a little better, although it might move around on you, so be careful with that. But here's our scatter diagram. So there's nothing more to it than that. It does all the work for drawing a scatter diagram for you, just by simply having this table. So what type of relation appears to exist? Well, to me, that's a pretty strong linear relationship, right? We can see makes a pretty strong linear relationship. And it definitely is negative. As the weight goes up, as we move along the x-axis, the y values go down. So this would be a negative linear relationship. Okay. Now what we can do is we can compute the correlation coefficient to get a better idea about this. So if you go into stat, advanced, and then linreg is what we're looking for. Linear, that stands for linear regression. And if we tell it where our variables are, so x sub 1 and y sub 1, it'll give us three things here. It'd actually give us three things here and then more things. So first of all, it draws the line for us. Don't worry about that. We're not actually, we'll talk about that in the next section, more about this line idea. This is the number we care about. negative 0.964 is going to be our R value. And then R squared is just another value of how strong a linear relationship is, or a relationship is. And then residuals are simply the z-scores that were used to calculate this. So you can put those in there if you want. It'll calculate them for you and tell you what they are. But all they are is a residual is how far is this dot from where it should have been on the y-axis based on the line. How far off is our line from what actually happened? Okay, that's so like, for example, with this, let me see if I can find this point. It's going to be hard because I can't really read what these values are, but well, actually, I could just click on one. Let's click on one. So if I click on this one, that's this 398418. Its residual is 1.15315. So that just means it's 1.153 above where it's predicted to be by this line. So the actual value was 1.153 above its predicted value, which is what this line's doing. And we'll talk more about that in the next section, but I thought I'd point out what those mean. So, but for now, for section 4.1, all you care about is this R value, negative 0.964. And these R values may sound familiar because we have been using them with normal probability plots, right? And the closer those were to 1, the stronger the linear relationship, and therefore we could conclude that it was approximately normal. But so compute the linear correlation coefficient between weight and this, you get this R value. Does a linear relationship exist between the weight of the car and miles per gallon in the city? Yes. Okay. Because negative 0.964 is very close to negative 1. Okay, so that's the idea. So that's all there is to that. So here's another problem. So what I'd like you all to do is pause the video real quick, try this one on your own using the data that's in our Google Sheet, and then press play and see if you get the same answer, if we get the same answers. Okay, so now you guys have had a chance to try this. Let's go ahead and talk about it together. So we go into our data sheet, 4.1 problem 2, and grab our data. And I'll put it in here. And then we'll zoom in on that. Okay, so what type of relationship appears to exist, if any, here? Hopefully I got all my data right. Okay, and if you answered there doesn't appear to be one, then that would be the answer I would go with. There doesn't appear to be much of one. If there's any one, it appears that it goes a little down and to the right. But I would probably say no relation appears to exist. Okay, so let's see if the correlation coefficient backs us up on that. So let's do lin reg. So you can type that in by just typing in LIN. We'll get you here. So x sub 1, y sub 1. And so in this case, we get an R value of negative 0.164. And so we can say, does a linear relation exist? No. Because negative 0.164 is much closer to 0 than to negative 1 or 1. Okay, and so that's the idea of what you're doing in these problems. Okay, thanks for watching this video about section 4.1. Come back next time and we'll look at the linear regression part of this. We'll look at the line and how we can use that to approximate values. Don't forget to do your homework and your quizzes. And As always, if you have any questions, make sure you're sending me an email or a remind message, and we can chat. See you next time.